And with this, thanks you all for joining us today for our 10th Roundtable, the Battery MBA Roundtable, looking at a range of perspectives on the future of batteries. My name is Dr. Simon Enke. I'm the founder and chair of Battery Associates, and I'm extremely delighted to be here with you today to have some really exciting thought leaders from the battery space, from different aspects of the battery space with us. And yeah, I think it's going to be a packed, fun few hours, or at least 45 minutes for everyone joining us online. And if you're watching this right now on LinkedIn or YouTube, feel free to also introduce yourself in the chat, in the comments. Feel free to share where you're calling in from, share an interest you have with us as well. And hopefully you'll be able to submit some questions later on this way as well. So we really can make it interactive, because we would love to hear from you as well. But of course, let's get started. Who are the speakers today? Shada, do you want to kick it off?
Yeah, thank you very much, Simon. Welcome everyone to our Battery MBA Roundtable 10. We are very honored today to be with you, and we have very important names joined our panel today. So let's begin with introducing our panelists. And the first panelist is Richard BOUVERET. Richard BOUVERET has been at the forefront as CEO and chairman of e-mobility and smart grid initiatives at Blue Solutions, part of the BOUVERET group, since September 2022, with a deep understanding of vehicle life cycles, expertise in mechanics, and a keen eye for cutting-edge technologies. BOUVERET focuses on innovation within the sector, tasked with transforming Blue Solutions into market leader for solid-state batteries and electric buses. His expertise is vital in navigating the company towards future technologies. A graduate from École Nationale Supérieure des Mines de Nancy, BOUVERET brings over 30 years of experience from his time at Valeo and ZF Group, where he led development strategies, commercial transformations, merger and acquisition efforts, setting a strong foundation for his current role. For the second panelist, I will hand over back to Simon.
Thanks so much, Shada. And yeah, Lina Emilsson. She's a qualified and experienced chemical engineer and senior leader with a deep interest in clean tech, and she's passionate about having a positive impact for the future of sustainability. She's an experienced leader in early-stage battery companies, executing major programs and building high-performing teams. Currently, she's serving as the CEO of Nidec Energy, a pioneer in long-duration energy storage solutions, utilizing the 24M technology in the form of Freya cells. Previous roles include Northvolt and Britishvolt in cell manufacturing, as well as SaaS business CEO, and a broad experience from the pharmaceutical industry. Additionally, she serves as an advisor to clean tech startups in the battery industry. She's committed to sustainability and impact businesses to decarbonize the world. So Lina, big welcome to you as well. With this, over to you, Shada.
Thank you, Simon. So our third panelist is Abdul-Rahman Raji. Dr. Abdul-Rahman Raji, the Chief Technology Officer at Zeta Energy Corporation, brings over 15 years of experience in pioneering lithium-sulfur battery technology and carbon nanotechnology. With an impressive portfolio of more than 45 patents and research publications, alongside an H-index of 22, Dr. Raji is a distinguished figure in battery technology sector. His academic achievements include a PhD in chemistry from Rice University and a postdoctoral work at the University of Cambridge, where he led the establishment of Energy Storage Lab and the Dry Room, a cornerstone for battery research and prototyping. At Zeta Energy, Dr. Raji drives the technological vision, leading innovation in battery materials, cell engineering, and the commercialization of next-generation storage solutions. His work exemplifies a deep commitment to bridging cutting-edge research with practical technological advancements. With this, I hand it over to Simon again for Battery Associates.
Thank you so much, Shada. And again, big thanks for everyone joining us today on LinkedIn and YouTube, and of course, all this fantastic cohort as well of the Battery MBA. This is just going to be a super quick few slides about who we are as the organization hosting today. Battery Associates, you can see it here. Our mission is to create a sustainable world through the power of people on battery innovation. So we hope you're all part of this mission. And we do this in a couple of different ways, including Battery to You, which is our educational arm, where the Battery MBA is really our flagship program. So really fantastic to have all of you here from this cohort with us as well. Then we have Battery Pro, which is more consulting and recruiting services we're offering with that. And then Battery Lab, where we're actually developing our own hardware and software, mainly our battery cycler for battery testing. With this, over to you, Melanie, for the Battery MBA.
Thank you. As Simon mentioned, education and training make up one of our key branches, and Battery MBA is our flagship program. For those who don't already know, here's a quick overview. It's a CPD accredited 12-week online program that we offer 3 times a year. We have more than 460 alumni from over 50 countries, and more than 25% are female participants. The program is meticulously structured to accommodate full-time professionals with a manageable time investment of 2 to 3 hours per week. Our participant base represents a diverse array of companies actively engaged in different stages of the battery value chain. As you can see here, our alumni network includes professionals from leading organizations such as Tesla, Li-Cycle, PowerCo, Jaguar Land Rover, SVOLT, BASF, prominent universities worldwide, among many others. You can see here from the testimonials we receive, past and present participants have very diverse profiles, from research to manufacturing to policy. Our goal here is to help train this diverse and global battery workforce across the entire value chain. Have a look at the testimonial page for yourself to see how battery training has helped various individuals on their own journeys. If you're keen on joining our program, we invite you to apply for our upcoming cohort starting in May. Additionally, we're pleased to offer a range of scholarships designed to facilitate the inclusion of individuals from groups that are traditionally underrepresented in the battery sector. Another way we participate in the industry is through our own Women in Batteries events. We had an incredible Women in Batteries event in October featuring MBA alumni Dr. Crystal Waters, and we're excited to share that our next Women in Batteries event will be on the 17th of April at 4 p.m. CET for women and those identifying as women. You can see the event invitation on the Battery Associates LinkedIn page. Finally, we are excited to share that our 5th annual event, Battery Day 2024, is scheduled for the 26th of September. This full-day online event features leaders from various industries and showcases panels and deep dives on pressing battery developments. We cordially invite you to register using the QR code or the link provided here. Now, I'm going to turn it over to Simon and Zeta, who will be kicking off our roundtable.
Thank you so much, Melanie. Yes, and with this, again, we want to go to our fantastic panelists of today, Richard, Lina, and Abdul. And yeah, also an invitation already to all of our current participants of this Battery MBA. Feel free, as usual, put your questions in the chat. We want to get, this lively discussions going, which we had over the last 12 weeks or so now. And then, of course, also anybody online on LinkedIn, YouTube, please put your questions in the comments so we can address them as well. We try to get through as many as we can. From experience, time runs out in the end. So please be fast and put your questions in early. With this, over to you, Zeta, for the first question.
Perfect. Thank you. So for the first question, I want to turn to Richard, and I want to ask him about solid-state batteries. So the question is, given your leadership in solid-state batteries and smart grid technologies, Richard, how do you envision the integration of solid-state batteries in the e-mobility ecosystem? And what are the expectations of OEMs? So could you please shed light on the challenges also of scaling up solid-state battery technologies for widespread electric vehicle adoption?
Yeah, thank you very much first, Zeta, Melanie, and Simon for the introduction. Yeah, solid state, for Blue Solution, this is a story for the past 12 years of production, serial production. So we are not at the gigafactory, but we are producing serial product with a mega company, less than gigawatt hour. How we see that in the future, how we see the scale up. First of all, when you want to go to solid state, you need to master one part of the battery, which is the electrolyte, and you need to be able to scale up this product. You have a different technology. For us, we are working with solid-state battery with polymers. And the challenge is to develop a polymer that will work at the ambient temperature and to build, from the monomer to polymer, to build, from the scratch, a specific polymer that will be able to work at the right voltage, at the right temperature, and that will allow the battery to have to reach the cycle numbers imposed by the customers. If you take passenger car, very basic, 1,000 cycles, for example, and that this is something that we need to work. And the challenge is to be able to scale up the polymer, because when you build monomer to polymer, you are building few grams, and then you have to build half a kilo, and then few hundreds of kilo, and then you go for the tons, and then bigger. But then you need to have a different a partner to do that. And when a polymer is working for a few grams, doesn't mean that it will work for a few kilo. This is not so easy. Okay, science is good, but it's not so repetitive in polymers. Plastics are very, dodgy guy. They are playing with us. So we are working on that. This is one of the challenge as well. We have anode in lithium metal, but for us, we are at TRL9 since more than 12 years, and we're able to produce the quantity of lithium foil with 20 micron thickness, with +1, -1 micron specifications on kilometers. So that for us, it's something that we are able to even offer to the market, to the other battery players. And after, with that, we need to be able to create a polymer that will work nicely with any kind of cathode. And we have developed for us a new Gen 4, which is working now, and we have reached 1,000 cycle that can work with different type of cathodes, LFP, LMFP, NMC. The idea being agnostic to the cathode, because we will go to gigafactory, and the challenge is to go to giga problem become a huge problem in the future. So then we are working on that. Sorry, I'm talking too much on that, but this is our life on daily basis, and this is what I can share with you on that.
Yeah, amazing. Thank you, Richard, for that. Yeah, I understand the difficulty is really from lab to mass production. That is very, very real challenge for the OEMs. And thank you very much for all this insightful information about solid-state battery. So we can continue with Lina now. Simon.
Absolutely. No, thanks for the share. Yeah, I got a question for you, Lina, to kick it off. So Nidec Energy's partnership with Freya Batteries positions you quite uniquely in the low carbon station energy storage market. How do you see your innovative cell technology impacting the resilience and sustainability of global energy grids, particularly in regions with high renewable energy penetration? Additionally, what are the major technical and market challenges you anticipate in the next 5 years?
Yeah, great. Thanks for the question. Yeah, this is really exciting cell technology, spinning off of the 24M core technology and in through to Freya manufacturing. And this is really a game changer because they have so many, it's a fewer steps in the production. So they save a ton of energy, and they also save on the footprint. So making this really a good low carbon cell to then take further into the energy storage markets. It's very tailored to energy storage and the long duration energy storage. So we see that increasing now, especially with the solar integration, as you mentioned, Simon, where you're looking for longer duration batteries because you typically cycle solar throughout the 24 hours of the day, right? Where you charge during daytime and you discharge during nighttime, etc. So long duration storage is really on the up, and this cell is tailored to that long duration. There's also actually a great environmental impact here because this is actually PFAS free. And for those following the European legislation on PFAS, you know that is becoming challenging. It's a really severe, environmental poison, if you like, right? That we do not want to discharge to our waters or anything like that. And legislation might actually come in to to be a bit harsher on this as well. It's also NMP free. So again, another chemical that's a bit challenging from a legislation perspective, and health and safety as well. So there are other benefits to it. Then, of course, there are technical challenges. So following on the question here, it does take a bit more in terms of pressure management, temperature management, and we need to be a bit more sophisticated on the module level. So you actually have quite high tech on the module design that you wouldn't have to on more conventional type cells. Then, of course, there is a big market challenge in the energy storage space. What I typically see is energy storage is a bit behind on the ESG space. Customers in the market are not asking as much for low carbon, for sustainability, for ESG. Cost and price is still a major driver here. So it's really, really important to be able to penetrate the market also with a reasonable pricing, because the market isn't prepared to pay too much extra for good ESG credentials, unfortunately. I do hope this will change as the market matures as well, and that we will see a bigger sustainability drive. Of course, legislation in Europe is already pushing also energy storage in that way. And the market challenge we see today is the very challenging price levels we do have out of China. So obviously Europe and US needs to be able to meet those price levels or be close-ish, which is of course also why the IRA came into place, to be able to actually plug that gap. So yeah, but it's an exciting space to be, and energy storage is really, really on the up as we're putting more and more wind and solar power around the world. So we need energy storage for multiple purposes to, well, store the energy, of course, but also to balance the grid and make sure that we actually can integrate sustainable energy sources.
Fantastic. Thanks so much, Lina. And yeah, I think some really interesting thoughts we will pass on, or we'll tackle a bit later in the question as well. And that's just another encouragement to all the participants. I already see some questions coming in here in the chat, but also want to give the people online, I know there's quite a few of you. We can see probably one of our higher turnouts here, which is fantastic to see. Please don't miss the chance to ask your questions, because I think afterwards you're going to send me some messages and going to say, I wish I would have asked this question to the fantastic panelists. So yeah, please go ahead and ask your question now on LinkedIn, so we still have time to address this, because we have the first 45 minutes, which is public to all, and then the second part is only for the current Battery MBA participants. But with this, over to you, Shada, for the question to Abdul.
Thank you very much. So we start with solid-state batteries. Now we're going to transition to some other next generation battery technology, which is lithium sulfur. So my question to Abdul-Rahman would be, with Zeta Energy pioneering work in carbon nanomaterials-based lithium sulfur batteries, which replace actually conventional materials like graphite and NMC. What do you see as the primary hurdle and opportunities in transition from traditional lithium-ion battery technology to lithium sulfur technology at scale? And additionally, the following question would be, how does the environmental impact of lithium sulfur batteries comparing to conventional lithium-ion batteries? Can you please comment on that, Abdul-Rahman?
Yeah, thank you for the introduction, and really happy to be on this panel. I go way back with Simon since our days at University of Cambridge, and I've heard really fantastic things about the Battery MBA program from many executives and professionals in the industry. So really glad to be a part of this as a speaker today. There has been a lot of expectations about battery technology in terms of lithium-ion battery and how they'll play a key role in the industry in terms of cost parity between electric vehicles and the internal combustion engine. There are many forecasts or expectations that by this time of the decade already that this lithium-ion batteries should already reach cost parity. But what we've been seeing has been challenges from metal oxide-based technology in terms of the raw materials availability in the previous years, and also the rising cost of these materials, and more importantly, the forecast in challenges with availability and cost of the raw materials that go into the NMC technology, nickel, cobalt, manganese, and graphite. And also more significantly, the complex supply chains that's marked by geopolitical gamesmanship surrounding these materials. I think this opens a lot of opportunities for next generation battery technology, specifically lithium sulfur battery, where you're taking a low cost material, sulfur in this case, and then transitioning that to develop a battery technology that's low cost, that's widely available, and that could really offer a substantial value for widespread deployment of battery in electric vehicles in the years to come. One of the key things in lithium sulfur is, as you scale the technology, you're looking at sulfur and then the grade of the sulfur and the type of sulfur you put in your battery. And what you find is that as you narrow down on that grade of sulfur, where you're thinking, oh, but sometimes people try to purify and get the highest purity of sulfur. Well, the processes for purification of this, start to add cost, to the sulfur. So in a way that, might take away from some of the low cost advantage of the material. What we've done at Zeta is to see and say, well, we need to use sulfur from refineries, and we've actually taken sulfur from refinery. And the challenge from sulfur from refinery, because it's a byproduct, and there are many different grades and flavor within a given refinery and between refineries, and then developing a process that take advantage of this low cost sulfur. What we've done at Zeta was to develop our process around this sulfur in a way that the process become robust, where you're taking advantage of the fact that of these low cost materials, and make the process insensitive to variability in the raw materials, and preventing that variability but from being transmitted to the active material that comes from this sulfur material, which is very important in driving the low cost. That's very important to get widespread adoption. So a key part is that getting this sulfur, which already is a byproduct from the refinery, but also what comes with that is that you get more sustainability in terms of the environmental carbon footprint. You get low carbon footprint from this material. So I think the future of lithium sulfur needs to move in this direction, and the way we're approaching that is refining the processes and adapting the processes to become robust and insensitive to these variabilities, because the variabilities will happen. What you don't want is to have to purify the sulfur and add many processes to the sulfur purifying, which add to the cost, add to environmental carbon footprint as well. So that's one key part. The second part, the hurdle that has been prevented lithium sulfur in many years in reaching its fruition is the polysulfides that form on the cathode. Whereas you put lithium on the sulfur, you start to generate polysulfides that leach into the electrolytes, and it goes into the separator. In fact, in the past, when you open lithium sulfur cell, you see this yellow material that forms on the separator, and that could also migrate to the anode, where it could also degrade the anode as well. What we've done at Zeta is to attack the problem at the fundamental level, where we're creating bonding between carbon and sulfur in such a way that as you lithiate the material, you don't leach polysulfide into the electrolyte, and that enables long cycle life, which is required for electrification. I think this opens up opportunities for adoption of the technology. Oftentimes, people forget that in a lithium sulfur, you have two electrodes, the cathode and the anode. So not to forget about the anode, because it's very important. Lithium metal has been notorious for forming dendrites, where these tree-like structures that grow into the electrolytes, and then the separator potentially causing short circuits. What we've done is come up with a high surface area carbon material, where you carefully form a robust SCI on these forests of aligned carbon nanotubes, and then plating lithium metal locally on the sidewalls that's protected by this robust SCI, tens of nanometers of lithium metal on each nanotube, which enables long cycle life and also prevents the dendrite formation. So this key development, I think, creates unique opportunities for advancement in the field and removing the hurdles and barriers that have prevented lithium sulfur from being commercial reality, but also from the performance and also the low cost availability of the material. I think we're gonna see lithium sulfur become more and more an key industrial player in the years to come. Will you see lithium sulfur battery electric vehicles this year or even next year? Probably not. But as we move into the later part of the decade, 2027, 2028, this technology are going to become more mature, and with the developments and the price makes sense, the availability makes sense, and as you remove hurdles from both the technology and also the scale up, I think by 2027, this becomes a key part of how we drive electrification and achieve that cost parity with internal combustion engine, maybe even surpass the internal combustion engine vehicles with battery cost lower than $50 per kilowatt hour. That's really the potential with the lithium sulfur. In terms of environmental footprint, the great thing also about using, at least for our technology, is that we're using these hydrocarbons to make the carbon nanotubes. Now we're developing technology where we could use carbon dioxide as well to make carbon nanotubes, and this fits back in a way that reduces environmental carbon footprint to enable us to drive the technology forward. So I think both cost, availability, environmental carbon footprint reduction, in the years to come, software technology will play a key role in driving industrialization and commercialization as we get to look for more widespread electric vehicles in the industry.
Thanks so much, Abdul, and great to see you kept the passion from our good university days in Cambridge on this topic. So really good to have you. Thanks for that. And fantastic. So I think now we have already a couple more questions coming in online, as well as a lot of them here in the court, which is great to see as well. I think I will pass over to you, Shada, for the first question. Richard.
Yeah, thank you very much. So Richard, there is two questions for you about lithium metal batteries. So some of the companies, they're moving actually from they're moving to silicon-based anode instead of lithium-based anode, lithium metal-based anode. And what is your opinion on that? That is your first question we got, and we also have another question. If you want, you can comment on that, and I can ask the follow-up question.
Of course. Thank you, Shada. Very, very interesting questions. Yeah, it's clear that to go to silicon-based, it's and if you want to be able to produce battery, solid-state battery for tomorrow, I think today most of the company they will try silicon-based. That's because it's easier to move with that. I say that lithium metal today, we are doing that since many years. This is our core business. And for the people who have already touched lithium metal, they know the difficulty to produce, to laminate and to be able to produce at the right size. And after you have to manipulate it, okay, right, to make your battery. And that it's far, far more difficult. You need a very strong knowledge and long experience to do that. And I understand, but at the end, if you choose a silicon base, it's easier to do, but you will never claim the same energy density than the lithium metal, right? So it's a choice. It's just a choice. Less challenge but less density, or more challenge and more density of energy. So I think in the roadmap, for higher density, I think we will go first for a silicon base, then we will go to lithium metal. Most of the battery makers are doing that. For us, we decide to go directly to lithium metal because we are able to manage the lithium metal, right?
Mm-hmm. Yeah, we all know already Blue Solutions worked with lithium metal years ago, actually, with the polymer electrolytes. So the next question from the audience is can solid-state platform used with all chemistries that like LFP, NMC, lithium metal, and what is the preferred chemistry?
It's very, yeah. It is obviously it is good if you got one polymer that is agnostic to the technology of the cathode that you can put, because when you think manufacturing on giga size, giga factory, it's becoming a big headache to have different, I would say, polymers. Of course, that will be nice, or different other electrolyte that are not like us. But for me, I think, and we are proving that we are able to manufacture electrolyte today that will work at, that are working at ambient temperature, and that are able to go to the voltage of NMC, high voltage. So it's not a trouble. And I think if you all the time think manufacturing giga, what is the end of the manufacturing and how to make it simple, it is very important to have a one type of electrolyte. And this is what we are doing. And yes, we can work today with LFP, LMFP, and NMC. It's just if you want to have a battery with that will be more costly but more high density, then you will go with NMC. But if you want something a bit far more competitive, a bit less than I would say energy density, you go LFP. But keep in mind, a solid state battery lithium polymer 4th generation with LFP will be still far higher in density than the best of the lithium ion with NMC. So this is very important to keep that in mind.
Yeah, thank you very much, Richard, for this excellent insights. So let's continue with the Lina's question now.
Thanks so much, Zeta, and thanks so much, Richard. Yeah, there was another question from our audience, actually an alumni from the Battery MBA. Philip, great to have you here, and he's thanking you for the great introduction, Lina. So here's a question about the production, right? And I'm not sure if something you can comment on, because it might be less connected to what you do, but there's a question about shifting production from FREYR from Scandinavia to the US. Will it affect the carbon footprint? Is the question, as renewable energy share in the US is quite lower. Thank you. If there's anything you can share on that.
No, thanks for the question. I think that is very, very relevant. So, I mean, the product design and the manufacturing design as such is already a lot lower carbon than conventional because there's fewer steps and this is not as high intense in energy usage. I do not actually know exactly what energy sourcing will be on the table for FREYR in the US. It's in Georgia, but the DNA of FREYR is all around sustainability. So I can honestly not imagine that they would run any factory without having 100% renewable energy source.
Fantastic. Thanks for sharing this, Lina. I think then we have one for Abdul. Zeta, would you like to go next?
Sorry, yeah. So Abdul's questions. How are the challenges for lithium sulfur batteries being addressed? The solution of sulfur electrode, poor electrical conductivity, and special additives coating being used for? And how are the volume changes which are significant in such batteries addressed? And the other one is that when it comes to safety, how safe are they compared to sodium-ion batteries?
So what we're doing for the lithium, the polysulfides and electrode stability is really making a compound of sulfur and carbon. And this compound, we start with sulfur with some polymer, the type of polymer you typically see in making carbon fibers. And then we also have some carbon additives that are added in this precursor mix. So as part of that precursor mix, this carbon polymer eventually turns to carbon. And then you have additional carbon additives in the precursor and you have sulfur. So by the time you make that material and all of these different components react, you end up with a sulfur that's bonded at the atomic level with the carbon. So in the near vicinity of that sulfur, you have a carbon that's nearby, and you're not relying on some mixing, post mixing of carbon with the sulfur, where you don't have very good contact between the carbon, but rather the sulfur is bonded, strongly bonded to the carbon. So this is the way that we reduce the resistance and improve the conductivity of electrode, but also importantly create an electrode that doesn't leach out any polysulfides into the electrolyte. So it's a unique solution because it addresses both problems of conductivity and electrolyte stability at the same time. And the second part, in terms of the safety of this material, one of the things that we found in this structured architectured material is that we did some thermostability testing, and these materials don't start to decompose until several hundreds of degrees Celsius. With NMC, they start to decompose after a couple of 100 degrees Celsius. So they're remarkably stable in that sense. And we've done a lot of studies on this for also our anode as well, where we have the carbon nanotubes that enables us to prevent the dendrite from forming. So these two key parts, we see, the engineering at multiple length scale, from the atomic scale, from the electrode scale, and also at the cell level. At the moment, we're doing a lot of robust testing. We're collaborating with national labs, doing testing, abuse testing on our cells, electrodes, and cells. And in the months to come, we're going to be releasing results about this. But the foundation really, is there at the electrode level to drive that improved safety for the cells.
Yeah, thank you very much, Abdul, for explaining that, especially how you managed with your electro technology, you managed to stop the polysulfide shuttle, which has long been investigated as an issue for lithium sulfur batteries. So we have another question, which is for Richard. I can ask that quickly. BOUVERET solid state battery has about 20 minutes warm up time. Would you consider using fast direct resistance heater like EC power heaters to warm up the battery in 2 minutes? Why or why not, Richard?
Yeah, it is when we talk about the previous and existing solid state that we are manufacturing. They are used for city bus and different applications, that it's true required to be warmed at 80 degrees to allow the polymer that is used, the type of polymer to be warmed up, right? And we are using a system to warm them up. And of course, there is many new technology that we are considering to apply until we are able to put in the market the Gen 4 that is working at ambient temperature. Yeah, of course, we are very open to use any kind of technology to accelerate the warm-up. Warm-up is necessary for the people to know when you put your battery into sleep, okay? And when your battery is sleeping for days and days, when you want to restart to use it, and then you have to warm it, okay? Otherwise, when the battery is used, plug, unplug, use, you don't need to warm it. So it's the way, it's yeah. I hope that I'm answering on the question.
Yeah, that is perfect. And so we can now.
I think I can quickly, because I think I'm looking at the time shader. So I think we're almost out of time. So big thanks already for everyone joining us live. We're not over yet, but we're getting close to it. I just want to quickly say big thanks to also our speakers, but two quick things. So one is for our speakers, the next question I'm going to ask you, we're going to look at what is the future of batteries, right? That's the perspective on the future of batteries. That's today's topic. You all represent, I think, some really exciting technologies and industries, right, which have a lot of momentum, a lot of growth potential, etc. So maybe as closing remarks, which you could maybe lay out a bit, what is your perspective on the future and batteries to each of you as a closing remarks. And then also I want to say big thanks already for all the current Battery MBA participants who are having lots of questions. So once we finish in this live stream, we're going to continue on that. But again, for our live stream, for all of the people on LinkedIn, on YouTube, anywhere online, again, these closing remarks would be fantastic. And maybe, because Richard just went now, maybe we can do the other round. We start with Abdul, and then we go Lina, and then Richard.
I think as regulations, mature and catch up with the development in the battery industry, what you're gonna see more and more is more complete the request or requirement for more complete life cycle assessment in the battery industry. Oftentimes, people start their life cycle assessment from when the material enter their factory, while neglecting that the fact that there have been many processes on the material, on the raw materials. Take for instance graphite. You have the graphite mining, you have the purification, the refining, the shaping, and all of these different processes that lead to the release some impact on carbon footprint. But as we move on, all of this will need to be added in the life cycle assessment. And this, I think, will provide new opportunities for next generation batteries that are already addressing the carbon footprint or impact in the development of their materials and processes. So this is going to be a big part of how we move forward in the future.
Fantastic. Thank you, Abdul. Lina.
Yeah, for me, I think we're going to see a lot of proliferation when it comes to new technology and innovation, all the way through from novel materials through to really novel cell technology through to novel recycling methodologies as well. We already see all of these startups all across the world, right? As Abdul mentioned, getting your graphite or nanotubes out of your CO2, or there are other companies doing it from waste wood chippings and waste organic materials, for instance. And also all of these new cell technologies that will stop using harmful chemicals and actually drive a lot of environmental improvements also in the battery space. So I'm quite excited to see this. So it's not one solution fits all anymore. It's going to be a very specific battery world we're moving into.
Fantastic, thank you. And Richard.
Yeah, first of all, I think that battery, we will face in the future a big diversity. This is clear. We can talk about any kind of technology today, even though we are observing some mega trend on cathodes. You look at China and they are moving very carefully to LFP, LNFP, that will be done on cathodes. On the other side, on anode side and on polymer, on the electrolyte, of course, big diversity will come. But what is important, I think it's very important when we think battery, we have to have in mind all the value chain in the holistic manner. And I think Abdul was mentioning something important is when we talk about the raw material, the material processing, the component manufacturing, the cell, the module, the introducing that into the chassis or for e-mobility, whatever it would be, a passenger car or two-wheelers or whatever, we have to consider that in the holistic manner in the future. Because battery will not be electrochemistry in the future. Battery will be also associated to a strong ecosystem of, I would say, digitalization about power electronics. And that has to be taken into account. When you design your battery, you have to introduce inside the design to circularity from the beginning. The real added value in the future, the USP of the product will be there at the design point, if you have the courage and the will to really introduce that in the design of the battery at the beginning, from, I would say, from the mine till the full recycling, it has to be incorporated. And it's a very long number of equations, a system of equations for the mathematician to solve. With all these equations, you have a very few solutions, and we will have to work on that. And I think that the dual chemistry in the future also, or even more than two chemistry will come, because sophistication of power electronic, of management profile, usage profile of the customer will be very different in different country, different region, urban, not urban, and so on. So a lot of equation to manage, to sort out big diversity. And then it means we have to be nimble. We have to learn fast, and a lot of cooperation will operate, together in order to supply the right battery systems to the customer in the future.
Thank you so much, Richard. And I think with these words, we want to close it for the public part Again, a massive thank you for the fantastic panelists, as well as all of you out there on LinkedIn and YouTube and anywhere also you're going to watch this, I'm sure later on, some of you. So again, big thanks for being with us today, sharing your questions, your thoughts, and again, stay in touch. And if you're interested in the Battery MBA, feel free to get in touch. Quite a few of you already took the program maybe, but there might be some out there who haven't yet as well. So with this, we're going to stop the live stream. And thanks, everyone. Okay, I think now live stream is off and everyone can unmute themselves now as well. So everyone can relax for a moment. We're not live anymore. Hopefully everyone's feeling good. So again, and for free now, everyone to also turn on their cameras. We'd love to see you. So also the panelists realize you're not in a vacuum. There's actually people here. So great to see you all. Glenn, Raus, Albert, Samuel, Nitin, fantastic. Karima. Adisha, oh, fantastic, Kristen. Okay, perfect. So big thanks. Hopefully you enjoyed the show. A bit of different than the last weeks, but hopefully you enjoyed that as well. So without further ado, of course, we want to go back to your question. I think Glenn has the first question. Glenn, do you want to go first?
Yes. So my question was, as far as the solid state batteries comparing to liquid electrolyte lithium batteries, how's the difference in fire safety? I know that a lot of times when batteries experience thermal runaway, it's the burning off of that liquid electrolyte that feeds the energy release continually. So how is the fire safety compare for solid state lithium batteries?
I can answer if you want, Glenn. I don't know if I may, because for me, this is you come with this first question, but this is absolutely the most important when you do battery, okay? Before talking about anything else, forget. We are not able to bring to the market a safety. It is clear that it will not work a long time, even your battery has super high density, fast charging, and so on. So, and I can speak with that because we have this experience in 2022. We have 2 batteries that burned, in the bus, and we, of course, we work on that. And it's, problem could occur. Luckily, no people were touched by that. Okay, no victims, but the bus was destroyed. And when you put battery with lot of energy inside, if you have a thermal runaway, you will have a huge issue. Okay, whatever is the battery, there is no, any kind of battery can burn. If people tell you it's not possible, don't believe him. Any plane can fall, but normally they don't. It's like the battery. Okay, so what we have faced to that for us for a solid state battery, for example, you know that lithium metal, the melting point is 180 degrees, right? And then if you have a polymer, the polymer, it depends on the polymer, but the polymer start to generate gas at 240, 260 degrees. And if you heat the battery 180, you melt the lithium, then you might create some short circuit inside, then the temperature will increase, and then you reach 240, 250, then you reach after 500 degrees full after you have the fire. Okay, it's like that. It's quite simple. For the lithium metal, right, and polymer. So I can talk about that. And obviously, for the safety, you need first of all to have a system where you have a very good FMEA, that you design your product, and you have to anticipate everything. But we are human, right? And then so far we make tests, we try to work on any possibility to create that with some tools, with some AI, and somehow to really imagine what could happen. Even it's 1 ppm, 1 chance per 1 million, you don't take the chance about it, right? It means that all your specifications that are safety, you need to have the capability that is CPK more than 2 in production, far more than 2 even. Normally you should be 2.5, 2.6. It's crazy to do that, but you have no choice, right? Also, you need to have electronic systems on it, and you need to have redundant system. Redundant, you need, it's like autonomous vehicles. You need to have a double system to check some parameters, some delta temperature, delta pressure, very quickly to identify it as soon as possible if there is a deviation in your battery. And that also, this is additional systems, okay? And after, you need also to put system to retard the fire. If it's happening at the end, you need to have something between your cells that will stop, but stop not completely. It's very difficult to stop the fire on the battery, right? You can reduce the time of propagations, okay, to allow the people to leave the vehicles at least. Okay, this is the really the last safety point, which is a catastrophe, but this is the last point. Okay, of course we are working on system to extinguish the fire. I cannot disclose that because it's subject to patent. It will come, but we have to work on it, and we won't be ready for the next, I would say, 2 to 3 years on something that will be extremely robust. Okay, so this is the question of, I mean, the answer of Blue Solutions.
Okay. Thank you.
You're welcome, Glenn.
Again, I think you had a second question, Glenn, right, about lithium sulfur energy density compared to LFP. I guess that's for Abdul.
Yes. Yes. How does the energy density compare to the current LFP with liquid electrolyte?
Yeah, so at the moment, the lithium sulfur energy density is double what you get from LFP. And in the future, it's going to be triple that number at the cell level. So in terms of energy density, this is driven by the anode material and the cathode material. So the anode using a lithium metal, which has a lot of capacity. Of course, oftentimes people say, well, lithium metal has 10 times the capacity of graphite, so you'll have 10 times energy density. That's not the case, because when you make a cell, you have to consider all of the different components of the cell. You have the lithium metal, you have the cathode. The cathode also have a very high capacity, about 5 times, over 5 times the LFP. But yes, even though you have 10 times anode capacity, 5 times cathode capacity, you don't have 5 times or 10 times energy density. So you have to consider the electrolytes, the packaging, and all of the different components in the cell. So at the moment, what's demonstrated is double the energy density of LFP by my company and some other companies who work in the lithium sulfur space. But in the future, we'll see 3 times the energy density of LFP. And as I mentioned earlier, you won't see lithium sulfur in electric vehicle this year or next year. It takes some time to mature the technology and scale the technology and do all the different refinement and development, as well as the safety testing that will enable insertion into electric vehicles. So yeah.
Thank you.
Great, thank you. And I think the next question is from Lester. And then Shada, if you want to ask the next question.
Hi, yes, thanks very much. In terms of, in view of the fact that it takes a long time to explore for, permit and mine any minerals around the world, I'm just wondering what metals should mining and exploration companies be focusing on to future-proof themselves in the future? Because the last thing you want to do is have certain chemistries arising and developing, and there being a lag between supply of those metals from the mining industry.
I can go on that. Yeah. So there are some metals that are important, or that are still present in the different technologies. Oftentimes people don't talk about copper. Copper is a key component, and the availability of the copper, it's in many ways, it doesn't, no matter what technology you use, you're still gonna need copper on the anode side as the current collector. So that's is a commonality among many different cell chemistries. On the cathode side, you have the aluminum. That's the typical commonality on that side. So having continuous stream of these 2 components is very important. And of course is the lithium. The lithium is gonna continue to be a significant part of the electric vehicle industry for many years and even decades to come. Many different technologies, lithium metal, lithium sulfur, lithium ion, they all rely on lithium. So having that supply chain of lithium in the near future and also in the long term become very important. Of course, there are some new technologies like sodium ion, and where people thinking about the supply chains for that. However, in terms of the energy density, sodium ion just hasn't been able to to catch up with lithium based technology. And what's going to happen is that in the future you have multiple technologies that play a key role in the industry that really won't be just one technology, but rather collections of different technologies. And in battery development, people often, they say, well, when you have your new technology, you need to demonstrate high energy density, high power density, long cycle life, all of these different things. But the reality is in collaboration with off-takers and customers in the industry, that's when you start to narrow down on what the cell specifications need to be. Some customers are fine with say 300 watt per kilogram with a couple of few hundred cycles or things like that. And some they want high energy, then as high as possible, but they don't care so much about cycle life. Some they don't care so much about energy density, but they care a lot about long cycles and cost and things like that. So there's going to be multiple technologies, but there always will be some commonality: copper, aluminum, lithium, that will underlie many different technologies in the years to come.
Brilliant. Thank you very much.
Yeah, I'd like to add on that, dude, that was very interesting, because I share many points about the copper and aluminum for the current collectors. And this is a decision that we have taken a few years ago in design. I was speaking about we have to design and think about recycling and think about sustainability, and you do it at the beginning. So, for example, for the current existing Gen 3 that we are producing today, we don't use a copper for the current collectors, because we have developed lithium that is self-sustaining. We can use it without any copper. So, and this is the way that we are doing for many reasons, because we don't want to use copper, because copper is a very strategic material. We have already lithium, so let's be focused on that. And then we are able to make it very thin, and we use as a I would say current collector as well. It's anode and current collector itself. And of course, it was a challenge, because to do that, it's not easy. But as I said, if you work in the holistic way on the design, on the process, then we were able to do that. Regarding the other material, in our perspective, lithium, obviously for us, for lithium metal, is very, very, very strategic. And we need to understand and to check all the value chain to be able to speak about, for example, to get spodumene from Australia, from Canada, but also we can get other, I would say, lithium on water base from Chile or other place. But the idea is all the time to check how we extract that, because coherence in the way, if we speak about sustainability, is to be sure that extraction is done with the most cleanest way. There is never a clean way to extract. Please understand me. But we are trying to do with the best way. For example, direct lithium extraction, because you take the water, you try to reinject. It's not very good nowadays, but we are working on that to be sure that we are able to send back the water instead to go in the air. Otherwise, all the city around and all the ecosystem fully drying up. And that we are working on that. It's also one approach of coherence in your design. Take care. And the best way to optimize is not use it. If we can have making battery by getting rid of some raw material, this is the best way. Because to find a mine, it's 15 years when you find it. If you find it, and if you have 100% success rate, you will have your material 15 years later. It's not like doing a gigafactory. You need 5 years. It's something that is very, very important to integrate in your design.
Absolutely. Thank you.
Thank you very much, Richard. Just maybe, Lina, do you want to add something on the raw material side before we go to the next question?
Yeah, so I think, I mean, raw materials is always going to be so critical. And I guess just one point on raw materials for me that I think is very important, on a bit of a tangent, is more supply chain related, and making sure that we as an industry can localize properly and actually drive sustainability through that way, and then actually embrace new innovative materials. The battery industry has traditionally been very conservative, right, and not wanting to try new raw materials or these crazy new materials that are around. But I think we have a responsibility to actually drive our R&D in cell manufacturing and beyond, to actually help these new companies that have really cool technology coming. So driving our R&D with the purpose of actually getting new technology in there is super critical, and then localizing and making sure we have the ecosystem close to us. And this requires, cross-company collaboration.
Yeah.
Thank you very much for this addition, Lina. And we continue with Varun's question. Varun, do you want to ask your question?
Thanks, Shweta. This one's for Dr. Raji. A very quick question on what your thoughts are in terms of substituting the NMC and FP part of lithium batteries at the moment with sulfur when you start to commercialize this technology. How easy is it to substitute it? Is it a complete overhaul of the entire process, or is it just tweaks to the existing gigafactory processes to commercialize this?
Yeah, that's a very significant question that we've spent a lot of time addressing internally. So in the cell assembly, I'll start from there, because you mentioned gigafactory. We have most of the processes are identical. Of course, to the extent that within the current battery manufacturing technology, there are differences even within lithium ion. One manufacturer does not have exactly the same process as the other manufacturer. There's always some difference that are customized for the particular technology, but also for the particular process that's being used by the manufacturer. To that extent, we have those differences. But in terms of cell notch, electrode notching, winding, or stacking, or welding, all of these different processes, they're very similar to what we have in the current battery cell assembly. That's on the assembly side. Of course, we also have some advancements that we've made in areas like formation cycling. You still need similar type of equipment to do it, but we found ways to actually do faster formation and aging, where we could do faster. So at the end of the day, give or take, between one gigafactory and another, there may be 5 to 10% difference in the process, and that's no different when you talk about lithium sulfur battery technology. There are some aspects as it relates to materials. They're different materials. From the cathode side, at least from our standpoint at Zeta, is that we're using equipment and technology in terms of the rotary kiln, and you come in with the powder, and then the powder goes through the processing, and then you come with the active material at the end. And that's very standard in the industry. It's similar to what you get in the LFP technology. So the cathode technology is very similar in terms of manufacturing the active material in that sense. In this case, of course, the raw materials are different. You have in our case, we have a sulfur, a polymer, and some carbon material as the raw materials that feed into active material. From the anode side, that's different than graphite. Graphite is a multi-step process that has about 30 steps before you can actually get the graphite electrode. We're doing that in 2 steps. So we have the first is depositing a catalyst layer on copper, where this catalyst. So you start with your copper, it comes into the line, you deposit the catalyst using the similar technology that you use to in some packaging industry. So it's called metallization. In the packaging, they typically deposit some metals on cheap bags, cheap package. So we use similar technology, physical vapor deposition, to do that. So this is a low-cost technology. And in the second step, we'll be exposing this catalyzed copper foil to hydrocarbons, and in the future will be carbon dioxide, and then growing the carbon nanotubes there. So and you're coming out at the end with your material done. We also have technologies where I think where there may be perceived difference between the existing manufacturing know-how is in where the lithium comes from. So after getting our anode material in these two steps, which is a big improvement from the way graphite is made from both sustainability and carbon footprint standpoint. But people often ask, where does your lithium come from? which is an important question. A lot of the developed, you could lithiate the carbon nanotube at that point, where there are many different techniques that we've developed, and we have techno-economic models of those different techniques where you could lithiate you have a lithiated anode where the lithium is coming from the anode side, but we also have technology that where we lithiate in the cathode as well. And this would lithiating the cathode, in this case, one of the attributes of our cathode is the ability to lithiate the cathode, where you can have the lithium on the cathode side because you don't have the polysulfides. So that enables lithiating the cathode as well in a way that's stable. So in this case, it's somewhat, if you go with the process with the lithiated cathode, then it's identical to what you typically have where the cathode is already lithiated in LFP or NMC. At the end of the day, what's going to drive this is the techno-economics of this, where your lithium is coming from, whether it's the lithiated anode and lithiated cathode. But we have some indications that lithiating the cathode may be a lower cost alternative or lower cost way to do it, but also it could offer a way to serve as a drop-in solution to some or combination, because when you have lithiated sulfur-based cathode, then you can also, then it becomes agnostic in terms of the anode. You could go with the lithium metal anode or some other anodes as well. So that could open opportunities for combinations, unique combinations. Yeah.
Excellent. So shall we continue now with Mahmoud's question? Mahmoud has two questions, one for blue solutions, one for lithium sulfur, I think.
Yeah. So for blue solutions, are you already investigating combinations with lithium nickel manganese oxide? It's high voltage and it's already cobalt free.
Yes, we are doing a lot of tests in this way. And of course, we have some customers that are requiring cobalt, and we are working with them, but we are very, I'm convinced with my teams that cobalt free is the future. We try to work on that, and we have many options. Even with the, I said with the LMFP, we are very, very happy with that, but we will work with other solutions that are using, I would say, stable and easy product than cobalt. Cobalt, we used it on extrusion, on dry extrusion cathode process. We are able to manage that. But to work with cobalt is a bit, I mean, it makes your people very scared, and you have to think about your team, you have to think about your people, and I'm not just thinking after where are going those batteries after, yeah, if they come back to you, it's okay, we can manage it, but you don't know. So, and the process is very dedicated. When you use it with cobalt, you can, it's really dedicated to that after, because it's somehow polluted. So we need to take care about that. So it's something that, and I would like to recommend, and we recommend to our customer to avoid that in the future,
Perfect. So we continue with the Q&A. So the next question I think is from Med. Med, if you want to ask your question.
I think Matt is not here anymore, so I can read it out for him.
Yeah.
Are there any notable shifts in anode materials that might affect the long-term demand for graphite? What alternative anode materials are currently being researched or developed that could potentially replace graphite in the future? I guess Richard maybe has some ideas, but maybe also others.
You know, we never use graphite. You know, it has been simple. So we, of course, it's a problem today for geopolitical reason or whatever. We don't want to use that, and we are not interested to use that. You know, it's very simple. After for anode, I cannot talk more. Maybe I have to let Abdul to answer, because we are very focused on, for the time being, on lithium metal. Even though we are working on other application, but for the next 2, 3, 4, 5 years, what we are seeing is lithium metal. Then after, other possibilities will come, right? So I don't know, Abdul, what you think about that.
Yeah, I have a few things. So we don't use graphite as well, as you mentioned. You know, the geopolitics of graphite is just very complex, but also the fact that we have a lithium metal, a lithium sulfur. I mean, in principle, you can combine the sulfur cathode, especially with the lithiated cathode. You can combine with graphite, but we tend not to go in that direction. So we have a lithium metal. Number one, you've got higher energy density when you combine with lithium metal, but we actually have a very efficient way to stabilize the lithium metal using the aligned carbon nanotubes, which enables us to plate the lithium effectively, also achieve long cycle life. But also, more importantly, the potential of being able to make the carbon nanotube using carbon dioxide, you know, holds promise to us from an environmental carbon footprint standpoint. When you look at graphite, there's so many steps in graphite, and the environmental carbon footprint, oftentimes people don't appreciate how much you know, this process, from both energy consumption and carbon footprint, is just, you know, staggering with graphite. And I think in the future you're going to see more and more people questioning the graphite you know, processes, and then with the new anodes that people are looking at, lithium metal, and now with you know, improvement in the lithium metal technology, either from the anode itself or from using solid electrolytes, either polymer solid electrolytes or inorganic solid electrolytes. You're going to see more and more shift from graphite in the years to come. I mean, you also have some people developing silicon anode as well, and some, you know, silicon combination with graphite, which reduces the amount of graphite, but there's also, you know, increasing, you know, amount of you know, percentage of silicon in those anodes. So yeah, I think in the future the concerns about graphite availability and will be lessened, because of the there are going to be more you know, other alternatives. Does that mean there won't be graphite at all in the future? I think there will still be graphite. It's just that the fraction, it's not going to be, you know, the overwhelmingly dominant anode in the years to come.
Yeah, perfect. Thank you very much, Abdul, for these insights about anode chemistry as well. So next question is Garima. Garima, can you ask your question? I think it's for Lina.
Yes, thank you, all of you, for the very interesting insights. I wanted to ask about grid storage. So what is the interest in redox flow batteries? And also quickly add, what would be the interest in second life applications of lithium-ion type batteries?
Yeah, I think the redox flow is very interesting for battery energy storage. And I think you posted in the chat specifically about Norway as well. So they do have, so Bright Batteries, I think, is a startup who's actually put some redox flow batteries already into use, which is quite interesting. And I think we're going to see all different technologies actually in energy storage as well. We're already seeing quite a big shift, you know, away from NMC through to LFP, LMFP, although we're not quite, you know, abandoning NMC as such yet, right? We also have the rise of sodium ion, which is actually coming now, which is quite interesting to see as well, which also matches the kind of low cost envelope that you do need to meet for energy storage. So I think that's quite interesting. On the second life, I'm one of those who are a little bit skeptical of redeploying EV cells to a second life in energy storage, because I mean, the energy storage market now is its own market with its own performance requirements in its own right, if you see what I mean. And those cells are very, very different. And we are now starting to see, you know, requirements for 20 years of life of a BESS system, right? You wouldn't get that out of a second life EV cell. So I just don't think that they're not, from a performance perspective, suitable, and the lifetime just isn't there anymore. So you're probably better off having a very, very high efficient and sustainable recycling process, so you can actually get the minerals back out again and create the you know, custom-made cells for specific purposes, if you like.
Thank you.
Thank you, Lina and Garima, for the question. And I take Mahmoud's question now because it's related to Nidec again, so we continue on that.
Yeah, if I remember correctly, with Nidec, you had a lot of BESS projects in Scandinavia. In your experience, what other hotspots or what are the emerging markets like Africa, Middle East, India, and so on?
Yeah, this is quite interesting. I mean, current markets, yes, Scandinavia is a big one. Also, UK is extremely large because of the high level of wind power. Germany is on the rise, and US. So they are the current big ones. But as you mentioned, Africa, I personally think that's quite interesting, because obviously creating microgrid solutions, you would enable to electrify, you know, small villages and very rural areas without having a grid problem at all, right? So I think, you know, they're probably better off, right? They're off grid and they're creating their own microgrids, which is an incredible opportunity for the future. And actually also in societies in Europe, if you like, right? Because a council could also have their BESS system and their solar panels and actually power their council with sustainable energy and set this up. So see, I think we're seeing, you know, if we're challenging business models around energy and the energy grid and the kind of old regulated status quo, where we would see more of these kind of microgrid solutions with sustainable power, wind or solar. India is another really, really emerging markets here. They are super on the rise. And I also work with Lina, or worked with Lina Energy in the UK, who has a sodium ion cell, and they are actually industrializing in India because of the high temperature. So their cell is optimum at high temperature, which is of course the case in India. So you would really think that any country with a lot of sunshine would do really well in energy storage and microgrid solutions and setups. So, you know, challenging that status quo old business model kind of thing of the traditional Western grids.
Excellent. Thank you very much, Lina, for those insightful comments. And we continue with the next question. It's from Nino. Nino, if you don't mind asking your question, otherwise I can do it.
Yeah, thanks, I can do it.
Yeah,
so my question is about lithium sulfur. And if it's true that the only benefit from them is just the energy density, because we are not talking about power density of them. So I know that they can do only very little C rates. Is this true?
In the past, this was the case, but with the recent developments in the technology, we've actually done a lot of work to lower the resistance of the cell, but also to lower the diffusion barriers in the cell, both diffusion and also activation, that you have a better charge transfer. What we're seeing in our electrode is on the cathode side, with this sulfur that's connected to the carbon, so you're removing or lowering the charge transfer resistance, but also we have a lot more control over the particle shape and the particle size and the way that we bring these particles together. So we can have primary particles, we can aggregate these primary particles into secondary particles. So with better control of the structure of the material, both on the cathode side and also on the anode side, where we have this porous carbon nanotubes. So we're actually seeing very high power in this application that wasn't attainable in the past. So it's a combination of improvement on the cathode side as well as on the anode side as well. And one of the concerns, or one of the things that the hurdles that have prevented fast charging or high power in lithium sulfur was because on the anode side, if you charge too fast, you have the risk of forming dendrites. So by having an architecture that prevents that dendrite formation, that opens opportunity to be able to charge fast, very, very quickly. So this material advancement certainly has helped in being able to reach not only long cycle life or energy density, but as well as fast charging or high power in the lithium sulfur chemistry. Yeah, of course. There are some. Go ahead. Yeah.
I wanted to ask, can you give me some numbers? What do you mean with high power?
So
Like
we've done testing in a small form factor cells up to 10C. And we're developing cells, large form factor cells. For large form factor cell, it's not so much the C rates that's the main issue. It's how you design the cell for thermal dissipation, because you already have high energy density cell, and if you think about 1C for 400 watt hour per kilogram cell, the power will be higher compared to a cell with 200 watt hour per kilogram. Even both of them at 1C, it's double power. So how to manage such kind of power in high energy density cells, especially in a large form factor cell, become very, very important. And when you're charging or discharging very rapidly, in having a cell architecture that enables you to move out this heat without getting any hot spots. So number one is the cell design, but also there's a big aspect also on the electrode design, the tolerance of the electrodes, because what happens is that in the electrodes, the effect of non-uniformity in electrode coatings become more significant, and you can get a hot spot. And this hot spot is certainly, you don't want that from the standpoint of thermal dissipation. So from small form factor cells, no problem. You get 10C, but as you go to large form factor cells, the tolerancing and manufacturing and cell design will play a crucial role in realizing high C rate at for large form factor cell, the types that you see in electric vehicles.
Okay, thanks. Thank you.
Perfect. We're almost at the end of our questions. I think there is one more question, which is from Bharat. I can read it. It's for Richard. What is your thought on bipolar materials as current collectors for solid-state batteries, Richard?
Yeah, okay. I cannot disclose too many information on that because some of them are very confidential. But I would say that in the current collectors, what we are using, and I said that I think today that we are not using copper for the anode. We are able to get rid of it for the anode, and for the cathode we are using like the others aluminum, right? putting different type LFP, LMFP, or NMC. Okay, so we are there today. We are not planning to change the aluminum today because we don't have a better solution. You know, you think about cost, you look efficiency, you look everything. So we are there today. We couldn't find solution. You know, if it was my dream, I would have find a way to get rid of it as well. You know, as we have done on the anode side, but we cannot. So this is something that we are working, but I don't foresee any elimination on our own technology, even on the Gen 4 of aluminum, for example, for the current collectors. And whatever we are using, if it's with the chemistry of today, chemistry of tomorrow, or dual chemistry, which I would, and it's linked to the previous question, we will work with chemistry for high power on one side, more with sodium, and with high energy density with, I would say, lithium metal in the other side. So yeah, but no change on that.
Great.
Okay. Oh, sorry, Simon.
You're good. No, thanks so much. For more people to drop, as usual, we'll take our quick group photo. So anyone, please turn your camera if you want to be on it. And some people already drop off because we're a bit later today than usual. Still some people coming. Christine. Perfect. Okay, 3, 2, 1. Cheers. Awesome. Thank you all for joining. And yeah, just with this, also we have a feedback form as usual. Please in the chat submit that. It always helps us to improve these sessions. So we do appreciate that. And also just want to say a big massive thanks to our fantastic panelists of today, Richard, Lina, and Abdul. It was absolute delight to have you with us. So really appreciate you being with us and sharing your insights with this current cohort. And yeah, we also have then, this is the final week of the program. So hopefully see many of you at the graduation on Saturday, which is, yeah, it's a fun timing with Easter. So hopefully some of you can join us and maybe we can do some Easter eggs or something. We have to think about what we maybe can implement in this special edition of a graduation. But hopefully see many of you there. And then please also join us in the office hours for the case study presentations, because I already have received fantastic feedback of some of you who really enjoyed these. And again, even if you haven't been in part of the case study track, please join to see these other case studies. It's a really fantastic, yeah, outcome you will find there. Some great case studies have been developed by other participants, so don't miss out on that. With this, massive thanks to all of you. Thanks again to our speakers, and see you all very soon.
Thank you for having me.
Thank you.
Thank you very much.
Thank you.
Thank
Bye.
you.
Thank
Bye-bye.
you.
Bye. Bye,
Bye.
everyone.